Hello, am I audible? Mm. Hello, I guess we'll wait for some more time for more people to join. Let's start. Yep. Hi, how are you all? Mm. I'll wait till the number of people are 20 at least, then start. Joseph, why today was final rounder? Isn't there 6 rounds this year? Last year there were 6 rounds. Cool, I guess we'll wait for like till 25, then start. Loki, even I wanna go check Josa now and compare with last year's. Ah, yes, this session is independent of the previous one. The collab link I will send afterwards, after the session. So y'all are in college or like starting or are in school? Cool, cool. Okay, so I guess I'll start now. So when I say computer vision, what is the first thing that comes to your mind? Yeah, guys, what do you understand by computer vision? Could I get some replies? Like in a very basic sense. Well, the whole idea behind computer vision is that we try to make machines see the world the way we are able to see it. And face recognition, yeah, it's a part of it. When machines do get vision, they can perform some really cool things, and one of them is face recognition. Any other any other idea like what else can machines perform if they have vision? Like systems using computer vision. You have like several autonomous systems, like self-driving cars. You can also classify objects. Recently, like even in waste disposal systems, they're like using computer vision so that they're able to segregate waste more properly. Yes, pattern recognition is a part of it. I'll get to that. So yeah, computer vision is basically making machines able, giving machines the ability to see, just like how humans can see. And it can perform several things like classification of several objects. It can also be used for monitoring like several remote systems, such as like bridges, aeroplanes, ships, everything. And Like you said, pattern recognition is one of the most important aspect of computer vision because computers are not able to see the world the way humans are able to see it. Now, if we see an image, like take an apple, if we see it, we're able to recognize that it is like sort of roundish in shape and it's like red color, so it's gonna be an apple. But computers cannot see that pattern in one go. Have you heard of this art form called pointillism? It's basically drawing using points like dots. So when you look at it in a very close, like zoom in and look at it, it's going to not make any sense. It's just going to be a bunch of random dots. Um, but then if you zoom out and see the whole picture, you can see a certain pattern. You can see what image is exactly drawn. Now that is exactly how computers are able to see it. They're not able to see the whole vision. They're able to see it in the small dots. Like if you take this cat image over here, right? What computers see is this matrix. It's going to be like a huge matrix. If you zoom in, from this matrix, every single cell, it's called as a pixel. So every single pixel has a particular value of it. And this value ranges from 0 to 255. Why? So each of these pixels can store 1 byte of data. Now 1 byte means it can store 8 bits. 8 bits, 1 bit is a 0 or a 1. So if you do the PNC, you will see that the total combination possible is going to be 2 to the power 8. That's 256 combinations of values are possible. Is CV a part of AI? No, AI is a part of CV. There's a difference. Earlier, in classical computer vision, if you used to take like random filters, and then these filters were made through logic, and that is how we used to find pattern. But now we use ML to find these patterns. So technically, CV is not a part of AI, but AI has become a part of CV. Yeah. So before that, saying it's able to view this image as pixels as a matrix with multiple values from 0 to 220 to 55. This is for a grayscale image. Now, if you take a colored image, you're going to have 3 different channels: green, blue, and red channels. So in OpenCV, that is the library we'll be using, we use the channel of blue, green, and red in that order, BGR order. So now each of these channels will also contain values from 0 to 255. And our main goal is that we have to try to make the computer see these patterns from these tiny pixels itself. And as I had said before, we use filters, which are also again matrices itself, with certain values that are found through logic and mathematics. When these are applied, they're used to find particular edges or certain patterns, specific patterns like curves or like blurring the image. They're able to do particular things like that. Each filter has a specific property to itself. And what deep learning, that is the AI part, does is these filters are not handwritten, they are rather like automatically computed by the machine. They are learned by it. So now, before explaining further into what these filters do, I will sort of explain, to get like an intuition, I'll sort of show how OpenCV works. So OpenCV is that this is a basic Python library that is used for computer vision. It can be used for several tasks like opening the image, reading it, doing modifications in it like rotating, translating. You can also like draw your own images if you're very skilled at it. So in this part, we'll be looking at few basics like how to draw a blank image or like a few squares, rectangles, etc. So this is the code I've written in Google Colab for it to read an image. Now it doesn't have to be this big. When you're generally writing in your own editor, you can it'll barely be like 3 lines of code. But for Google Colab, it requires this cv2 underscore im show in order to project the image. This is the image that I've loaded, and this is the URL that I've taken. So I have not downloaded it. So this does the downloading operation of it. We are importing the OpenCV and NumPy. NumPy is also another package or another library within Python, which is generally used for computing mathematics, like using arrays especially. So once you download it, I'm skipping the rescaling part for now. We'll get back to it later. We have to make it readable by the OpenCV, so we convert it to NumPy arrays, and then we decode it for OpenCVs. Now I'm rescaling it, and using the cv2 underscore im show, I'm able to portray this image here. Now, if I were coding it in my own editor, then you would just need to import cv2 as cv, and then you would need cv.imread and put in your image path over here. Once you put in that image path, then you will have to do cv.imshow and load in the image tag that you want and select the image which you want to portray. So once the image is loaded, now I'm going to show how you can create a blank image in OpenCV. Like I had said before, they are like just a bunch of pixels with values in it. So if you define a matrix that is like full of zeros, that is what np.0 does. So np is that is numpy that I had stored before. It's used to create arrays and also operate in them. So now using np.zeros, I've created an array of the size 200 cross 200 cross 3. Now what this means is it is 200 in width, 200 in height, and it has 3 channels behind it. As I had mentioned, there are 3 color channels. To display a blank image, you don't really require 3 color channels, but I'll tell you why I've put 3 over here. Also, all of this is stored in a data type of uint8, which is basically like unsigned integer. It stores values from 0 to 255. Now 0 represents black and 1 represents white. Even in this, 0 represents black and 255 should represent white, but then we normalize it, that is we divide the entire thing by 255 so that we're able to get it from 0 to 1 range. And now we can also paint this by specifying particular pixels that we want it to be painted. So we specify red, we copy this blank image, and then we run this one first. Yeah. So now this is just a colon, so it's going to select the entire width and the entire height. Thus we're able to see the entire image became red. But then if you like specify a certain amount of pixels, like from 50 to 100, and then that is for the width, and from 50 to 100 for the height, then you can you'll get a painted region of only that particular set of pixels. You can also draw rectangles using cv.rectangle function. So again, you copy the same image from before, and you specify 2 vertexes. One is this and the other is this that I have specified, and then you can put any color. This is in the BGR format. So see, if you put a higher color of B, and these two if you keep like a lower color, 55 and say 80, and -1 is to fill the entire image. Then you'll get a more blue color of an image, and you can also change the border. I think I exceeded the pixel limit. Oh. Similarly, you can also draw circles. Circles, you'd copy the same image again, and then you specify the center of it, specify the radius of it, and you also mention the color of it. And this can also be filled, so you get a circle. And you can also draw lines. You specify the initial starting point and ending point, the color and thickness of that line to get a line. And we have seen grayscale images and we have seen BGR images. We can also convert between these color spaces in OpenCV using this CVT color function. That's to convert the color. Now here I'm converting from this BGR to grayscale. So you write in the function CVT color, you mention the image that you want to operate on and what kind of operation you want it to do. cv.color underscore BGR to gray converts it to BGR to gray. Then if you portray it, it's going to give us a gray. Generally in Python, when you say -1, it is to select everything, but it's like the default values for your question. Yeah. And it's also a HSV scheme. HSV scheme is generally used when you want to separate a particular color or particular hue out from the remaining background. Like say you want to separate only red color, then if you mention only the red color's hue, like HSV has 3 digits, like the first one represents the color, the second one represents the saturation, and the third one represents the brightness. It's like this. The first one is the hue, the second one is the intensity, that is the saturation, and then the brightness. If you keep the brightness and the hue intensity the same and you just change the hue, you'll be able to capture only that particular color which you wanted to capture. Now here converting this BGR to HSV, it looks kind of like not what you would expect to see, but it works. So yeah. Also another thing to note that only OpenCV is the one library that is using BGR color, and the other libraries in Python are using RGB. Like if you take matplotlib, firstly I am just putting in the image normally without converting it, and you can see that this RGB image is portrayed in matplotlib as BGR, because matplotlib doesn't know that we are giving it an BGR image. So now if you change this to the RGB form after converting it from the same function, then it will be the same. And like I had said, there are 3 channels: blue, green and red. And all of these 3 channels can be split differently using this cv.split. Now I have split it, and also I have portrayed the shape of it. This is the normal image. You can see that it is 267 pixels wide and 400 for height, and it has 3 channels. But then this is the blue region that we have captured, and this one does not have 3 channels. It has only a single channel. And the region where there is blue, it is generally lighter compared to the region where there is no blue. Similarly, here where there is more green, that is lighter compared to the region where there is like no green. And red also the same. Here there is blue, so it's kind of dark, and here there is red, that's kind of light. So it's like wherever that color dispersion is more, that color is going to be seen as light and the other side is going to be seen as dark. It's like how you would have seen in like middle school science experiments where you keep a red object in a blue room, like a room with only blue light, then it's going to be visible as black. And also you can merge all of these again together using the merge function. Now if you create a blank image, which I have created using this function here, now this img.shape is the to captures the dimensions of it, the width and the height, and it ignores the channel of it. And when we are merging it again, we put only the blue channel here, and then the red and the green channel we leave it as blank. So when we do that, we get only the blue channel visualized as we would have expected to see it before. Same with red and green. So this is like the basic functions what OpenCV can perform. Now we'll move on to filters. which I was about to cover. So like I had said, filters are these hand-engineered matrices. They are found using specific logic and specific maths to perform a particular task. Now, how do these filters work? When we are um, when we place the filter directly above the image and calculate the element-wise dot product, that is, you multiply this 0 to this minus 1, 0 to this minus 2, 75 to minus 1, like that, each individual pixel is multiplied, and then all of the multiplied values are to be added. Once they're added, they will take the position of the center pixel. So you see, they're changing the pixel's value itself to perform a particular task. So depending upon what kind of task you want, the numbers on this filter are changed so that the pixel you get as a result will also be specific to what you want it to do. Like for example, if you take a Laplacian filter here, this Laplacian filter is an edge detector filter. So we can take edges as points where the pixel intensity drastically changes. Like here it goes from white to black, right? So the intensity of the pixel is drastically changing. And when you apply this filter over an area where the pixel intensity is all the same, then you're going to get a 0. Because if you see, the sum of all of this is 0. So and 0 represents black. So all of this is going to be black. Similarly, when you place this over here, right? Try adding the values and see. You will get minus 1, here minus 1, and 4. So you will get 1. And 1 is white. So this edge is depicted as white. And if you place it over here in these three, then you are going to get minus 1. However, you will be considering the absolute value itself, because there's nothing such as a negative pixel. Darker shade for other colors for only blue versus, and like I said, wherever the quantity of blue is more, that will be lighter. And wherever the quantity of blue is less, that will be darker. Yep. And this filter that we have used here is called as a Sabel filter, and that is exactly what is depicted over here. It's also another edge detection filter. Remember I said it's the change in the intensity of the value that depicts the edge rate. And in mathematics, we use a differentiation as a factor, like a derivative is a factor that represents how quickly a function is changing. And so that logic is used here in order to find this filter. And another logic applied here is, if you see, the magnitude of the weights added to the center of this kernel is more than the ones above. Why? Because it can give a more accurate representation of the value we're trying to find for center. Since we're trying to find only for the center value, this minus 2 and 2 have higher values, so that it can give a more accurate result of what is going on in that particular area and not the ones above or below it. And the speciality of this filter is that it can be separated into two matrices, like two vectors, each of these vectors performing a particular task. One of them is finding this intensity difference using differentiation. The other one is finding smoothing the region out as we proceed. Because if you see, there is a noise over here. Now, if you applied this horizontal edge detection on it without this vertical layers, then it will give us a 0. But if you have these vertical layers, when you add all of them and you equate it, you're going to get 2, which means that it gives this area some kind of an edge. And the same, if you apply it on the others, this 3 or this 3, then you'll get like 4. Yeah, the intensity of the edge here is lesser, but the whole point is that it's eliminating the noise. And we'll look at, now I'll be showing like 3 different kinds of edge detections here, and you can see how each of them are varying from each other. This is just loading the image. Now for the Sabel function, we will be, we know that the Sabel function can calculate both positive and negative because it is in a gradient format, right? So Uh, yeah, so this UINT8 is not able to store the values of negative. It will just crop them at 0. And we don't want our edges to disappear, which is why we'll be storing this in this data type. So in cv.subel, we'll mention the image that we wanted to find the edges of, the data type, and which direction. One is the x direction and 0 is for y direction. This defines the x. And after we get all the pixel values that's calculated, including the negatives, then we make it into its absolute value. Like I said before, we don't have negative pixels. We use only the absolute values. Make it into the absolute and then you store it back into this data type. Then you get the subel x function. Similarly, you do with subel y also. So this is your subel x and this is your subel y. So if you see, when you move this filter across like this towards the right, then it's forming edges in a vertical direction, right? So if you move it in this direction, it's going to be computing these two. These two zeros are going to be vertical. So in those zeros places, you're going to be getting these vertical edges. And similarly, for the x also, the subel y also, you're going to be getting the x direction. And now here it's the bitwise OR operator that I have used. I'll be talking about bitwise later on in this session. But as you know, generally in logic gates, if you take OR, then it adds on it takes like the intersection as well as the non-intersecting part of the image and adds it on. In logic gates, if you see according to the truth table, that is how it works. So yeah, you combine these two and you get this image. And now we had previously seen the Laplacian filter also. Now what the Laplacian filter does is in subel we did a single derivative. In Laplacian it does double derivatives. Because of doing double derivatives, it kind of increases the noise in the image. So it's not able to get the clear picture that subel is able to get. Like it's way more less intense. And there's another edge detector called Canny Edge. This is one of the most famous edge detectors. So here you have like threshold values. You have to apply like 125 and 175 as threshold values. So if the intensity difference is like greater than 175, then it's going to confirm it as an edge. If it is less than 125, then it's going to be it's not going to be an edge. But if it is between these two, it's going to look at the neighboring pixels and see if those are like above 175 or not, and then it's going to decide. Now the algorithm behind the maths behind this Canny filter is kind of like you apply subel filter and repeat, and you get Canny filter. So yeah, that's with the edge detection. So any questions? I hope you got the darker color answers, like the question you had asked for. Yep. Okay, then I'll explain blurring. So in general, if you take blurring, it is like not the center pixel, you have a center pixel, but you're going to consider the values of all the pixels that is around it and then create a pixel for create another value for the center such that it kind of smudges it, right? So you're kind of like taking an average of all the pixels that is around the center pixel. But then for Gaussian blur specifically, it's derived from the Gaussian function, which kind of looks like this. So the center element gets more magnitude, like more weight compared to the ones that is around it. And it's also divided by 1/16, sort of like that averaging scenario only. And the sigma is the standard deviation of this Gaussian filter. So based upon the sigma, your kernel size varies. So if your sigma value increases, your kernel size also increases, and more it increases, the more blurring it performs, and vice versa. So blurring is another method that is used to reduce noise, and it's also used to perform augmentation. No, Laplacian doesn't cause blurring. It is for edge detection, right? It kind of gives like a drawn with a chalk sort of image, but see any filter, if the sum of it is becoming 0, it's going to be an edge detecting filter. That's why for blurring, the sum of it is not becoming zero. You're kind of getting an average of all of them. Yes, each blurred pixel does go to a new array. They are not put in the same place again. They're computed differently. Yeah, so for blurring, there are 4 different kinds of blur that I've shown. One is the Gaussian blur, averaging, and median. So averaging is what I was talking about. It generates like a 5 into 5 kernels containing like 5 to 5 matrix containing only one. Then that entire one is multiplied to the pixels behind it, and then it's divided by 9. So it gets like an average of it, and then it portrays it. You can use cv.blur to show this image. And similarly with yeah, as you can see for Gaussian blur also, here also we've used 5 into 5 kernel size only. However, the blur for Gaussian is much lesser than the one for averaging, because the weights here we've used is higher. The weight for the middle one is going to be 4, and the one around it is like 2, 1, and 2, right? So you're kind of giving more importance to that center pixel itself, because of which the blurring of it, the importance of the other pixels around it is reducing, so its blurring is kind of reducing as well. And yeah, for median blur, unlike averaging, you get the median of the values. So you again multiply it as you multiply it normally, and then of the 25 values that you get, since this is a 5 into 5 kernel, of the 25 values that you get, you find the median of it, and then you put it. And this is one of the blurring features that I like the most, because it kind of like maintains the edges while it is blurring. Now, how does it maintain edges when it's also blurring, right? So for this, in the bilateral filter, you pass in the image that you want to find. And then this 5 is again the kernel, sort of like the kernel size, and you can take it. The ones around it is measuring. And this 15 is known as the sigma color. Now, what does sigma color represent? It gives the weight to that particular pixel depending upon the difference between its color intensity. Now, this was not there in the other blurring features. Now, if more higher the sigma color value is, the more higher weights it will give to that particular pixel because of the difference. And this is known as sigma space. Now, in this 5 into 5 kernel, if you see in Gaussian blurring, it sort of like gradually reduces as it moves away from the center, right? And that values are fixed. But here it is not fixed. As you move away from the center, you're able to set how, like in what pace do you want it to reduce by. So if this is higher, then you're going to be reducing at a much faster rate. Wait, no. If this is higher, then you're going to be reducing at a much slower rate. So the ones at the farther end will be getting higher weights. Sort of like that. Basically, the last one is for blurring color. Yes, the last one is for blurring the color and not the edges. Then we have some affine transformations. This includes like rescaling, translating, rotating the image. Then it's also more like performing shear and stuff. So generally we use these transformations as a pre-processing step before we feed it into an ML model. There could be multiple reasons. One is called data augmentation, if you know. It is like you want to generate more images and more cases so that the model is able to understand all kinds of scenarios. Now, if you take a camera that is moving, right, it's not going to be moving steadily, capturing all the images perfectly. It's going to be shaking. It's going to be, it's going to give like tilted images. It's not going to be the same perfect way. So we kind of like perform transformations to it. And the math behind this is like fairly quite easy only. It's like simple matrix multiplication. If you take for rescaling, this is the matrix multiplied. It's gonna like scale it down based upon the sx and sy. and to translate it, it's gonna just add an extra value to the original image to see how much it can translate. And similarly for rotation, we have a rotation matrix. I think like most of you who finished JEE will know how a rotation matrix is calculated. And when we include the center of rotation and the scaling factor, that is the point about which we want it to rotate and by how much we want it to shrink or enlarge, the scaling factor, then we get this matrix. But how are we getting that? We first fix the rotation, the point about which we want to rotate, and then we translate it. So this is the translating part of that matrix. You just translate it, and then you rotate it using this, and then you translate it again back to its original position. So when you multiply all of these together, you get this. Now when you multiply it, obviously it'll be a 3 into 3 matrix, but then for performing rotation as well as translation, we can't use a 2 into 2 matrix. We would require that variable 3. So we have a 2 into 3 matrix in order to save memory. So this part of it, this alpha, beta, alpha part, is only performing rotation, and this other larger part of it is performing the translation. And to perform these affine calculations, we will be using warp affine, that is the function that is used for this. So we'll start with translation first. We're defining a function for translating. We are giving it inputs of the image, the x and the y. The translation matrix, we had seen in the slide also, this is a similar matrix as what was seen in the slide. We just define that matrix as well, store it into this data point, and then you mention the dimensions. Now 1 is used for expressing the widths, and 0 is used for expressing the heights. And the dot shape is an attribute of this image object. So you find the dimensions, and then you put it into this warp affine function. Now what warp affine does is it does the matrix multiplication. So you give it the image, you give it the matrix that you want it to be multiplied with, and then you give it the output dimensions that you want. So it gives, I've given 50 and minus 50. Now a conventional difference is that you put minus y, it actually goes up instead of going down. As you can see here, I've already put it minus 5, it has gone up instead of coming down. This empty space was where the picture used to be before. And same with rotation as well. You're defining a function for rotating it. You have to give it the point about which it's going to rotate and also the angle by which it needs to rotate. So yeah, if none of the rotation point is mentioned, it will be taking the midpoint itself as a rotation point. And it's taking a floor value so that it gets an integer, because pixels are not in integer format only, they're not in decimal formats. So the cv.get rotation matrix is used to make the rotation matrix based upon that formula that we saw before. So in that formula, we had to mention the angle, and we also had to mention the rotation point, and we also had to mention the scaling factor. So after when we provide all of this, the matrix is generated, and that matrix is again used in this warp affine function itself. We're giving it the image, we're giving the rotation matrix, and we're providing the output dimensions in order to get the output. Yeah, and as you can see, it's rotated. This one is 75. So I have to run the top functions first. It rotates by 45. Yep, that's basic rotation. Now why did I skip rescaling in the beginning is because I wanted to introduce you to this warp affine function. Now for rescaling also you can use warp affine, but it's kind of unnecessary because you have another function called cv.resize. So in this, you give it the frame you want it to resize, you give it the dimensions you want it to be resized by, and then this interpolation is basically the maths behind how this image is being formed. You give it like, I wanted to use this particular set of mathematics to use it. So yeah, those kind of laws. Yeah, so you define the scale, you're changing the dimensions as you're multiplying it by the scale and the width. and you're getting this. So one, you can use this function, that is a rescale function, or you can use the scale function, which I have written using this warp affine itself. And third, you don't need to do either of them. You can just where is this? You can just directly write it as cv.resize. Give it the image you want it to change, and also the dimensions you want it to be, and the interpolation method. Yep, then it transforms it directly without any need of any of these functions. Um, Another reason why I wanted to show you this scale function is because I kept mentioning that this dimension is the output dimension. So then when the dimensions of this input image changes, we want the output image dimensions to also be the same. Now in translation as well as in rotation, we are not we're keeping it the same. Because of that, when it is moved by a certain amount, right, we are getting this black space. Now if you don't want to get this black space, we have to change the output dimensions as well accordingly to how it will change. Like here we are getting a view scale, right? So if I use scale, then the black part and the image are perfectly coinciding. But then suppose I change these values slightly, then they're not going to be coinciding. You're going to get a black space here as well. That is the main idea I wanted to show about what an output dimension is and what the input dimension is changing by. Yeah. So that's it with the affine transformations. And yeah, I had said before that I will be explaining the bitwise operations as well. So why is it called bitwise? Because it is operating at a bit level. How does affine know whether we are scaling or rotating or transforming? It's based upon the matrix that we provide. Warp affine only does the multiplication. The matrix is what is doing the actual work. Yes, so getting back to bitwise operation. Um, it's called bitwise operation because it performs the operation at a very bit level. As I said before, each pixel contains like 8 bits. So it can be any combination of these values. So then it compares 0 and 1. So if you apply 0 and 1 with AND, then it's going to give us a 0. And same with every single one of these bit, it calculates with every single one of these bits and gets a value out. Same with OR and same with XOR, same with NOT. And I'm sure in the previous sessions you would have learned about these in the logic gates part. So I don't think I need to explain this. Yes. So why are we learning these bitwise operations in computer vision? How are we going to be using it? So this bitwise is used for this masking purpose. Now masking is where when you have a particular image, you want to have a section of it alone. Like you have a sunflower and you want the flower part alone, you don't want the stem. So you're going to mention, you're going to mask it and get the flower part alone. But then more than for images, it's for like videos. You have like a ball moving around. Then if you apply masking to it, it will be able to follow the ball around wherever it goes by taking the non-intersection and intersection meaning. I will tell you it. Yes. So that is basically why we're using bitwise here, so that we get a particular isolated region, or we're able to extract some information out of this image. For bitwise, So I have generated an image of a rectangle as well as a circle. And now this intersection part. If I put and, right, if I operate with bitwise underscore and, then it's going to give like between in these two images, whichever part is overlapping, it's going to give only that section. That is what I meant by intersecting regions. And non-intersecting, if you take or, right, then it's going to take the entire image. Whichever part is intersecting and whichever part is not intersecting, all of those are going to be displayed over here. It works the same manner in which it works in the truth table. Wherever you see there is like at a bitwise level, if it's like a 0 and a 1, it's going to give you 1. Wherever it is 0 comma 0, it's going to give you 0. Same way is working for OR also. Same with XOR as well, is going to give you like XOR is basically it gives the opposite of AND. That's how I remember it at least. So if AND is going to give you all of these sections, so XOR is going to give you all the non-intersecting sections. And not just does the opposite of whatever input it is given. Now for circle we have given, earlier the circle was white and the outside was black, so it just inverts the pixel values. Take rectangle. Yep, the rectangle also same. So any questions till now? I think I've seen. Okay. And now how is this bitwise operation applied to masking? So you generate, read the image normally, and you specify a mask that is like a rectangular region. You generate a blank image and you make a mask, a rectangular region in the blank image by mentioning it's one of its edge, the other edge, and also the color and the minus. Yeah, the color and -1 to fill it. And when we apply this mask operation, we're using AND over here. So we're going to give it as image, comma mask equals to mask. Why are we giving image twice? Why can't we just like over here we just give rectangle, comma circle? Why can't we just give mask, comma image? What will happen if you just give mask, comma image? Well, the issue is the mask is kind of like a 2D array, whereas the image is actually a 3D array. So like you can't compare both of them with each other. So here what we're doing is when we say image and image, we're comparing the image with the image itself again. So it's going to give us the same image back, and we're applying a special condition of mask over here and giving it this particular mask. For clarity, I think I will remove this. Just mention it as M, and you can just say this is mask is equals to M. So we're taking this white region alone. So what a mask does is, wherever there is white in the back, it generates the image only in that part of it, and wherever the rest part where it is black, it generates nothing, it's just black. So this mask basically just makes like a white and black and white binary image sort of thing, and that is used for classifying or finding specific sections of the image. Morphological operations. These are very useful actually. When you want to remove noise, right? Then you would be using morphological operations. There are two main morphological operations I'll be talking about here, that is erosion and dilation. Just like how it is in the name, erosion does, it removes the edges, like sort of like erodes the edges. It Yeah, it removes the outer section of the edges. How does it do that? It has this kernel one of filled with ones, and it multiplies to the pixels behind it, and whichever is the minimum value that you get over there, that is replaced for the center. So now if you apply it here, right, the minimum value you're going to get in this pixels could be 0. So it's going to be replaced by 0. That's why when it's eroded, you see most of the area has become like black. And only some of them where there's like more higher white ka weightage has stayed white. Otherwise it has become black. And for dilating it, you basically, instead of minimum, you take the maximum value of it. Yeah, so you see that it has become like sort of like a darker white region over here when you maximize it. Now, the main purpose, like in this image, it's not really depicted that properly. But if you have like some small white noise patches here or there, and you want to remove them, right? Then if you erode it, and after eroding it, by eroding it, you're going to remove the small white dots while you're going to maintain the bigger white dot. Like when you apply a mask, right? You're going to get like a whole region that is going to be fully white, and then you're going to get small points of whites. So it's going to remove all the small points of whites, just going to keep the bigger points of white. And then when you dilate it, since the smaller points are no longer white, they're black, they're going to stay as black, and the mask which you had before is going to get back to its original size. That's the whole purpose of morphological operations, which I have also done here. So for applying morphological operations, I've kept the canny edge of this. I've calculated the canny edge of the gray image of this. And as you can see in dilated, it's going to give like much thicker values. And for eroded case, it's going to give like much lesser values. Now the 7,7 is the kernel size, the filter size. It's a matrix of 1 which is of 7 to 7 size, and it's running over 3 iterations. It's running over the image 3 times. The same with erosion as well. You can use cv.erode and use cv.dilate and calculate that. That is with it. And yeah, I will be showing the attendance now. You can take the attendance. Tell me once it's done. Yep. Done is it? Fine, then I'll move on to the next part. That is contour detection. So what is contour detection? Now we have the edges of an image, right? Once we get the edges, those edges alone are not enough to describe what exactly the image is trying to, what shape it is trying to show. So contour detection does precisely that. It finds the exact pattern what it is showing. So how it is doing it is first of all connecting all of these edges together by seeing which if they are of similar intensity, similar shapes. So it's gonna connect in that manner. After connecting in that manner, these also have like hierarchical levels. Like you take a rectangle, and then inside a rectangle you have another circle image, and then inside the circle you have another square. So it has a kind of a hierarchy that builds over, right? And based on this, it also performs some sort of like a shape analysis, and it finds the moments of it, finds so you can find the centroid of it. That is basically what contour detection is. So it takes all of these small pieces and it joins them together. For contours, now contour detection can be done only on edge kind of the object which has only edges, right? So we convert it into the canny edge format. But there's another format you can convert into, I will tell later. So yeah, you're just loading the image, you're finding the canny edge of it. Once you find the canny edge of it, you're finding the counters using this find contours uh, function. So what this find contours does is it generates the list of all the coordinates or points where there is a possible contour, like every single small segment there is, and joins them together. So kind of generates the entire list of all of these small segments that is there. So we describe on what image we want to find the contours, and then the cv.return-list, it gives us this particular one gives us the entire list of all the contours. But then there's something called cv.return-external. So for the external one, it gives us only the external contours and does not give the ones internal. Like I said, there are hierarchies. That is what this hierarchies over here is defining. We don't want the internal one, we want only the external one, then you can use that. And there is something called tree as well. I mentioned it all here, you can go through it later. So in the tree one, it also gives all of the contours but organizes them into each of its hierarchical order. And the cv.chain approx, what this does is it gives us a method of approximation of finding the contours. Now if we take a single line, we can either consider like all the coordinate points of it. That is what this one does. It considers all the coordinate points and gives them out. But then if we use something like cv.chain approx simple, will be mentioned here, then this gives us like only the starting and ending points. So since I said that contours is like a list, right? So you can also find the length of the lists. And using canny edge, we've gotten like 61 such contours. And instead of canny edge, you can do something called as thresholding. So thresholding is a form of binarizing the image. Binarizing as in you convert it into like only black and white format. There is no in between, it's just pure black and white. So ret represents return and thresh is the threshold image. So when we say cv that threshold and pass in the grayscale image, and you mentioned the threshold values also, that is 125. So anything that is above 125 pixels is going to be directly classified as a white color, and anything that's below is going to be classified as black color. And we're giving a thresholding type that is binary, that is for binarizing the image basically. So now using this same this thresh image, also we can find the contours, but when we find contours using this thresh image, we are getting only 36 contours. So there is a decrease in the number because the edges are probably not that defined right in this sort of like joint, you see. And these contours that we found, these 36 contours that we found, they can also be drawn on a blank image. So I created a blank image, and then using cv.draw contour, I generated on this blank image the contours as a list that all the coordinate points it has wherever there is. So all of its coordinate points, this -1 is to indicate how many of these points you want, and we have chosen -1 because in Python -1 indicates everything. So, and the red color for the color that is there, and one for the thickness of the contour. Now if you see, all of them are like sort of joint, right? And if you take edges, they are not very joint, they are like separate. That could be because of the thresholding as well. So that is what a contour does. And we mainly use these contours for segmenting an object. And displaying it. Now I will be showing you a program based on everything that we have learned until now. And this is going to be a program of it detecting like tracking down wherever a ball is moving. So this is the code of it. And yeah, if I run it, oh wait, I forgot. Yeah, So you can see it's tracking down exactly where the ball is going. It's returning the center values, it's returning the radius as well. But it's not like that accurate, like it's a little bit displaced because of the shadows and stuff. It can be showing deformations. Now when you like close it, you can't really like see, like estimation points is not given, it's just like none, right? And if you have like two different objects, yeah, if you have like two different objects, it's not going to be able to detect the smaller one. It's going to only be able to detect the bigger one. If you have like two small balls and you want to detect it, then also you won't be able to detect it. And this only it doesn't give like depth and everything. It gives only the 2D information. So yeah, that's basically what this program is doing. So I'll be explaining what exactly is happening. So here, the main function that we have used, this find ball function that we have defined here, is what is segregating the yellow color ball from the rest of the background and portraying it as a mask. So, like I said earlier, HSV is used for such kind of tasks. So we use convert it into an HSV image first. After converting into an HSV image, we make a mask of two particular color ranges. So we make a mask of this HSV frame along with these two color ranges. This color range, as you see, it is in a hue saturation value format itself. So only the saturation and brightness is remaining the same, and only the hue part is changing because yellow has like multiple shades, right? So in order to account for all of that, we have specified two different types of hues. So we make a mask of all of these. This HSV along with in range, as in the range of this yellow that we have mentioned. So it's going to make a mask of that. And like I said, we're going to erode it first and then we're going to dilate it to get rid of noise and then again build up the image. Yes. And then we use the CV to find contours to make the contours. Here we're using only the external contour because we want only the outside part of it. We don't really want the inside of it, right? So we're going to be using that only. And we're going to be calculating the center and the radius using these contours itself. Now when we use CV2.minimum enclosing circle, it's going to find the maximum contour, like a proper contour that is in a circular shape. And it's going to measure the x and y of it, the center of it, and as well as the radius of it. What happens if you skip erosion and dilation? Then it's going to start recording noise behind it. Now I had only a yellow ball in my hand, but if I had like multiple yellow dots behind me, like multiple small sunflowers behind me, then it's going to be detecting like all of those as well as points in the mask. So you won't be able to get only the ball alone. You'll be having much more noise in the background. Yes. So as I said before, in contours we can find the moments as well. Now, what is a moment? Is basically like the weighted sum of all of the contour pixels, kind like in physics you would have studied the first moment is like the centroid, the center of mass, and its second moment is like the moment of inertia, like that. So here the 0th moment is the measure of the area and the first moment is going to be the centroid. So using that we're finding the center and as well as we're finding the radius which we get from this minimum enclosure circle. Then this is the main function which is responsible for capturing the video. I taught you how to read the image before, but this is for capturing a video. You mentioned a 0 here, cap is equals to video capture 0. 0 is for the webcam. Now if you want to use a particular video you have in your storage already, you can mention the path over here and that will work as that. And since a video is like a series of images, we will be using a while loop. So while the video is being taken, it captures every single frame and returns them. That is the RET comma frame, right? It captures every single frame and returns them. If it is not returning, then the function will break here itself. And the center, the radius, and the mask is what we get from this function that we have made before. After we get the center, radius, and mask, this part is the drawing part that we had done before. We put a circle around it. We put the bigger circle around the ball based upon its center and its radius. And we gave it a color and thickness. And we put a smaller circle at the center of it, which is like, we just gave it like a radius of 3 because it just indicates the center. And you can also put the text. The text was running at the side of my page. If you had seen, it had the radius as well as the center continuously being printed. And it shows the mask as well as the frame. You would have seen the mask. It was like a completely white page, right? Yep. And yeah, you apply a wait key of 1 millisecond. It is so that there is like the 1 millisecond wait between like a frame that is currently running and a frame that is going to be loading. And this is like just the it's like a standardized value that you press Q, then it's going to like break the screens, and it's going to release all of the screens and destroy all the windows. You're going to be using the normal name equal to main. You're going to be calling this function, and you're going to be running this. That is basically the breakdown of this code. I will send it later. Yes. And we saw that this has like several problems in it still, right? Like I said, if it is like not visible, if it goes behind an obstacle, then it is not going to be able to make like estimations. And it doesn't give any 3D information. You can't keep multiple images together and it's not going to give us a value. And you have to set up so many tuning parameters, like yellow color, meaning I have to set up only those yellow shades only it can take. What if I wanted to capture like more number of more different colors of balls? Then I won't be able to do that. And also based upon the lighting and shadow, if you notice, my circle was not exactly on the ball. It was like slightly deviated. That is because of the shadow of my fingerprints falling on it. And to avoid all of like these kind of problems, and especially the fact that we have to make multiple different kinds of filters for different kinds of cases, right? We can't keep making so many filters for so many cases. We have to like let it be automated. So for that purpose alone, we're going to be using ML here, and that is how we moved from classical to this ML version. And we use this is called as a neural network. So we give it like an input, and that input passes through multiple layers. Each of these layers extracts a particular feature, like this could be like a right edge, this could be like a left edge, one could be like curves, one could be circles, and finally you will get like an image, okay, there is a circle and there is a line, and that could be like a number 9, sort of like that. So yes, kind of running it through, and you're going to, and all of these weights are also going to be automatically calculated. These filters are also going to be automatically being calculated based upon the errors that it finds. So that is how neural networks are now currently being, they're more than just neural networks. You can have transformer architectures, you have CNN. Someone had asked about CNN before. And there are so many such architectures which are being used and more developed also to find perform several computer vision problems like segmentation, object detection itself. You can take. Now here is like a very simple neural network. This does not have like any convolution in it, and it does not have like any activation function except for softmax, but that's not really in the network. It doesn't have any major activation function in it, so it's like performing just a very simple linear computation. So here we are going to take every single pixel values of this called as nodes and make nodes of them. So you're going to take each single value of it and you're going to align it into a 1D array. Now earlier it was like a 3-dimensional array. Now you're going to compress all of this and flatten it into a 1D array. After you flatten it into a 1D array, you're going to have a fully connected layer. That is, each one of these nodes is each one of these nodes is going to be connected to every other output possible. That is the thing about fully connected layers. Now in CNNs, it is not fully connected, It and also it doesn't like take every single value of it and like fully connect them. It uses this filters that I had showed before. It's called as kernels. So these kernels now run over the image, and it's going to give like a 2D instead of like a 1D array. So these 2D arrays then have like more spatial data. So that's the difference between convolutional ones and this one which doesn't have a convolution in it. So after getting all of these inputs and mapping it with every single output of this, now the output is calculated using a linear function that is b plus w into x. X is this array, and w is going to be the weights. Each one will have a weight, w1, w2, w3. So all of this will have particular filter weights, right? And after this is calculated, it gives you several. This gives you like 5 random values, like it's not gonna make any sense if you see those 5 random values. But then we'll pass it through a function called a softmax. And what the softmax does is it's a probability distribution function, and it gives you it takes all of these random values and it computes it in a format that the sum of all of them add to 1. So after you get the values of this, you're gonna have like the output you would want if the image was a daisy. It would be 1 0 0 0 0. But suppose the output that you get is going to be 0 0.6, 0 0.1, 0 0.1, 0 0.1, 0 0.1. Then you're going to have to calculate the error between them. Now there are multiple ways of calculating the error as well. Suppose we take just root mean square, then you're going to be finding you're going to be subtracting them and squaring them and finding the root of it, right? That is the root mean square of it, that error. And once the error is calculated, based upon that error, you're going to be changing the weights that were previously here. So initially the weights are going to be randomly chosen, and the more you train the data, like the more images it passes through and more iterations it passes through, it sort of learns these weights automatically based upon this error. So this error is then passed back to change the weights using an optimizer algorithm like you have heard gradient descent algorithms or Adams. So using one of these algorithms, it changes these weights values, and once it's done training, you will have these weights which are like almost like 99% they should give you accuracy. But in this simple neural network, you won't get it that much. In convolutional ones, you can get it. Oh, attendance I'll be showing again once, so don't bother about it. Yeah, so that's basically the gist of how a simple neural network works. Now we can apply like a you can apply like a convolution to it. You can have activation functions on it, which includes like it introduces some kind of like non-linearity. Like now it's giving a very linear function, right? So when you introduce like activation functions, it gives like a non-linearity to it. What is a convolution? The process we're taking a filter and then we're moving it all around the image. That's basically the process of a convolution. Yeah, in a very simple sense, you have those filters. When those filters move around, the moving of those filters is the process of convolution. So you can either have those kind of yeah, and those convolutional ones, they don't make 1D arrays, they make like 2D arrays, right? So because you're taking an entire filter of it. Yeah, so and there are like so many other things you can do. So, like there's another Python library. It has like several ML frameworks you can use. It's called MediaPipe. It's used for like pose estimation, and it can be used for object detection also. Like you have like multiple points in your body, it will take those values and it will be able to calculate the angle between them. You can try it out when you're free. and object detection models also are there, like YOLO or CNN. Now this basic simple neural network, I have attached the link over here. I'll be sharing this Canva link later, so you can go through that neural networks or training as well. And this is the attendance again. You can take attendance. Yes, I hope you all enjoyed this session as well. I really enjoyed taking it. It's my first time streaming. Yes, so I think I'll end the stream here if you all have taken attendance. Thank you.